T238 sent over one of their newest motors, which is a quick response, high efficiency, low loss brushless motor. This is the 25,000 RPM short version, which I'll be installing into my ICS LED6 A2 LSW. The packaging is pretty simple for this motor, and I just immediately noticed the warning on the back, which indicates not to use other brands of ETUs, not to power on in an unloaded state, not to reverse the polarity, not to use batteries greater than 12.6 volts or a fully charged 11.1 volt battery. Inside the packaging, you simply have the new brushless motor and the spring. Further specifications and details of this motor are available on T238's website. Overall, the outside appearance and build quality of this motor are very solid. To stay true to the warning on mixed matching brands of ETU, I also picked up T238's Razer Mosfet board. This is a relatively basic programmable Mosfet board from T238. In the box, you have the Mosfet, instructions, your signal wires, extra fuses, and a sticker pack. Just note this Mosfet is different than an ETU, which is an electronic trigger unit. For those of you that are familiar with the L86 trigger mechanism, it doesn't support any current ETU design out there, which is why for this build I have to use just a basic Mosfet. Main reason to use any Mosfet, even a basic one, is to allow full current bypass at the trigger contact. With the Mosfet, the trigger is operated on a minimal current signal line, and then the Mosfet directly powers the motor straight from the battery. This Mosfet also has other programmable features, but lots of them shouldn't be used with brushless motors, such as active brake or rate of fire control. The Mosfet also provides an internal fuse, low battery cutoff for better motor, Mosfet, and battery protection. Your first step for the motor swap is to prepare and disassemble your rifle to get at your motor. If you need to install a new Mosfet, now is also the time, but I won't be going over that in detail in this video. Looking at the T238 Razer Mosfet reminds me very much of the Gate Nano or MIRF series of Mosfets for its similar size and features. The Razer is slightly larger than the Nano Mosfets, but the Razer is also about half the cost and will still fit into most rifles. In fact, I currently have the Gate Nano hard Mosfet installed in my LED6. The T238 Razer Mosfet wiring diagram matches exactly the same as Gate Nano series Mosfets. For a full detailed installation video of this style of wiring on the LED6, refer to my Mosfet installation video for the MIRF 3.2 Mosfet. I'll throw a link to that video in the description below. In this video, I'll show you how to install a new motor, such as the T238 brushless motor. I'll also do some comparison with this motor, my current T238 brush motor, and a couple other motors that I've tried in this build. While doing all that, I'll also give you some feedback and my review of this motor itself. I'll warn you now, this video is a bit long, but what I've done is I made chapters in the description below, and you can use those to fast forward to any segment you'd like. My current motor is a T238 Star River motor, which is their high thermal efficiency brushed motor running at 29,000 RPM, under no load on an 11.1 volt battery. My current brushed motor is a slightly higher RPM than the new brushless motor that I'm installing, which is only 25,000 RPM under no load. Jumping ahead a bit, but the rounds per second of the brushless motor were surprisingly equivalent to the higher RPM brushed motor, and I think we have boost in efficiency of the motor to thank for that. If you want to see a full motor comparison and installation video for my original T238 Star River brushed motor, then check the link in the description below, as I have a separate video dedicated to this, including a bit of a comparison, also to the stock ICS Turbo 3000 motor, a G-High motor, and a Tinley motor. I wanted to throw this chart up on screen for those looking to tune a rifle rate of fire based on an 11.1 volt battery and 18:1 gear ratio. I know this is quite specific, but I've tested many motors out in this particular rifle build, so hopefully this chart will help somebody out in deciding what motor might interest them most. Some of the specs that I found online seemed questionable, so I threw a set of question marks beside them in this figure. One of my primary build goals for this rifle was to obtain a suitable rate of fire to sound aggressive enough, provide sufficient cover fire, but not to deplete the battery or ammo too rapidly. What I've found is that using 11.1 volt batteries on an 18:1 gear ratio, either of the two T238 motors that I've tried can easily achieve 20 rounds per second, which I find is the sweet spot in that aggressive sounding but not too ammo depleting world. With the new brushless motor, I expect higher overall battery life due to improved motor efficiency. One of the biggest perks of brushless motors is not having to worry about brush wear. This might not be a big problem if you only use semi-auto based fire modes, or play limited times a year, or just simply shoot with high restraint. However, brush wear can be a primary subject for typical rifle maintenance when you're using a full auto support platform, and an upgrade to a brushless motor can be a big quality of life improvement for your maintenance schedule. Brush wear can become an even bigger problem if active brake is involved. Other benefits of brushless motors include quieter motor operation, higher consistency, and smoother performance. Of course, the increase in efficiency, lower battery usage or current draw, and of course lower heat from the battery as a result. This also means overall longer gameplay out of the same battery. I put this brushed T238 motor installed in my LED6 through a whole season of fully automatic fire. This season I ran the rifle with the active brake off to help reduce motor wear. I estimate that I shot at least 30,000 rounds through this rifle, if not more. I wanted to take this opportunity to just check out the motor brush wear from the entire season of full auto and compare it to a set of brand new brushes just to see how it did. To check your motor brushes, just pop off the spring on the retention clip and pull the wire, which will pull the motor brushes out. The motor brushes are simply conductive carbon blocks that will wear out from friction as they rub on the commutator over time. While there is some brush wear here, surprisingly it looks insignificant, and these brushes still have a lot of life left. I'd have to credit this to turning the active brake off, because in my first season I ran this rifle with a different motor, and I had to replace the brushes after the first season, but in that season I ran active brake on. With the brushless motor, brush maintenance is one less item you have to worry about. For the L86, the short motor is contained in a motor cage. The spring that comes with these motors typically is too small to fit within the L86 motor cage, so hopefully you've still got your factory spring. If you haven't done it yet, now's the time to remove the set screw from the motor pinion gear and apply a bit of blue Loctite to the set screw. The motor pinion gear is pressed onto the motor shaft pretty tightly, but I've had the set screw come loose after extended motor use, and the screw actually shot off and jammed in my gearbox. Be sure to let your Loctite set overnight before using the motor. When you disassemble your current motor, just keep in mind which side was positive and negative, because chances are your wiring is already ran for that orientation, and if you install your new motor the opposite way, you'll have to twist your wires to make it work. It's better just to keep the motor in the same orientation. One other thing that I noticed when I set the motor into this cage is that the battery connection terminals on the rear of the motor were extremely tight against the motor cage. This would prevent my motor wire connectors from being easily installable, and I know for a fact that I would break them by trying to push this together once fully assembled. To solve the problem, I gently bent the motor connector terminals on the rear of the motor slightly outwards. Don't bend too much because these types of thin connections can actually break off really easily. When you install your motor into a motor cage like the ICS L86, you want to make sure that you can fur out as much free space as possible. As the motor engages the gears and enters resistance, the motor itself will kick back a bit and rotate. Even under its own torque, the motor may kick in the housing. This actually causes things to go out of alignment and will cause some premature wear in the system. There are probably more sophisticated ways to do this, but I found something as simple as electrical tape on all four sides of the motor is pretty useful in preventing the motor from twisting within its cage. If you have a better way to do this, let me know in the comments below. When you install a new motor, you always want to check the motor height and adjust to suit the new motor, and you'll see just why in a minute. To do this, install your bevel gear and place your motor as it would sit during engagement. It's always better to install the screws to secure your motor or grip in place so the alignment is true. But given the unique design of the ICS gearbox and motor cage, I can easily see the motor height by just placing things flat on a desk. You want to target the maximum contact and engagement between your bevel gear and the motor pinion gear teeth. Generally 100% contact's not required and probably is too much, but it should be no less than 70%. What I personally find is getting too close to 100 actually doesn't allow the gear and motor system to accommodate any flex, and that causes more problems. If you have too little contact or less than 70%, you'll experience a premature wear, likely on your bevel gear, but also on your motor pinion gear. Every build will be a bit different for the sweet spot range because a lot depends on your gears and gear shimming. Trial and error by sound, heat from the motor, rate of fire, and battery life are pretty good indications to determine what's best for your build and gear shimming. One issue that I noticed with this particular motor is that the motor shaft height is about 1 millimeter shorter than my previous T238 motor. I'm not sure why the motor shaft height was shorter, but what happened is the motor height adjustment was maxed out for this new motor, and I can just barely get that 70% engagement with the bevel gear. I'll be monitoring this closely over the season to see if it causes any premature wear. I've also compared other measurements of these two motors, and in general what I find is the brushless motors are longer than their brushed sisters because of the PCB or chip in the rear of the motor taking up extra space in the end bell or end cap. Anytime you install a new motor, you must check your shimming again, particularly the shimming between the motor pinion gear and the bevel gear. If any adjustments in the bevel gear are required, you then have to reflect this throughout all of your gears to maintain the same gear-to-gear alignment that you previously had. If your bevel gear goes up, then all of your other gears likely have to go up by the same amount, assuming they were shimmed correctly in the first place. Vice versa if your bevel gear goes down. If you haven't shimmed your rifle at all yet, this is the prime time to learn, but I'm not going to go through the detailed steps in this video. If you're lucky, you might find that your motor meshes very well with your current gear shimming, but that'll be very much dependent on the motor itself and how tight your original shimming was. I'm not an expert or the best at shimming, and it's largely trial and error, so I'm not going to demonstrate this full process by video. For this shim job, I simply started by checking how much play there is to press the bevel gear upwards towards the motor pinion. I try to minimize that play by adding shims on the bottom of the bevel gear. To detect the play, I use a fine tip screwdriver to press up on the bevel gear shaft, and then I detect the movement or play by pressing my finger over the opposite end of the shaft where it'll move up and down. You want to repeat this process till you feel you have all your gears shimmed correctly, and then fully assemble and test fire. Often the best way to figure it out is just listen by sound. For the other gear-to-gear shimming, the process is similar, and typically I try to target around 70 to 80% gear-to-gear teeth contact or overlap. You want to avoid getting too close to full contact or full overlap between gears, because this will also cause problems due to the lack of ability of the system to accommodate any play. If you get too little contact, something like less than 60% contact, you'll definitely start to put premature wear on your gear teeth, and you might even see full teeth failure or teeth chipping off. Another part of shimming that I haven't demonstrated is epoxying your bushings into the gearbox. I always prefer to do this as it helps eliminate noise potential from bushings spinning in the gearbox, and it also ensures that the bushings and gears sit how I want them to. If you do this step, just make sure you do it the night before shimming and let any adhesive fully cure before attempting shimming. As a final step, check the sector gear contact to the piston to make sure it's not binding. I've had a few problems with the L86 in this regard, and I had to use half-teeth pistons and even modify some of the gears so that they can work in this gearbox. This is actually just a function of the gearbox design. Most builds won't have this problem. As you check gear-to-gear shimming and plane your gears, make sure you screw down enough of the screws of your gearbox to hold it tightly closed, as if it was in use. Using finger pressure to hold the gearbox together won't be enough, so just avoid the temptation altogether. It's quite tedious, but you need to screw down the gearbox and open it up multiple times throughout this process. When you're finally happy with your shimming and the unloaded gearbox, it's time to reassemble it and do a full test fire. During the test fire, you want to make sure you listen to sound. If you're doing a lot of shots, you can check the heat of your battery to see if it's unusual. A more technical way to check the battery would be to check current draw during firing. Pulling too high of a current could indicate a poor shim job. Another sign on chrono could be going full auto and seeing a change or reduction in rate of fire from a previously well shimmed gearbox, indicating the system might be working too hard against a poor shim job. When reassembling, make sure you don't mix up the polarity of the wiring at the motor. This won't be covered under warranty and will likely cause damage to the chip and motor if you get things backwards. While I skipped a lot of details on the Mosfet and ETU, your best bet is to heed the warnings on the box and only use T238 brand Mosfets or ETUs. That said, other brands may work, and it's probably up to the tech community to provide guidance. I reached out to both T238 and Gate in this particular instance, and neither of them were willing to confirm compatibility or to provide any guarantees that anything would work. With any Mosfet or ETU brand, you want to tread very carefully on Mosfet features that cause variable power control, because it may send conflicting signals to the PCB chip within the motor itself and cause damage to the motor or damage to the Mosfet and ETU itself. I originally tried to use the T238 Mosfet as I showed to stay true to the warnings in the box for all of you. What I found was the T238 Razor Mosfets not very user-friendly to install, and ultimately I was not able to get a response out of the Mosfet in my final install. I resorted to using my previous Gate Nano Hard Mosfet, which worked very well with this brushless motor once I turned active brake features off. I do want to add that while I may have had a negative experience trying to get this Mosfet to work from T238, I provided my feedback to them to try to get some improvements out of the box, make it a bit more user-friendly for the average tech. They took my feedback seriously and provided it to the development team, and we'll just have to wait and see if they make any changes to this basic T238 Razor Mosfet. Finally, we can check the chrono results.
Oh, that is crisp.
One thing I noticed is on a nearly discharged battery at 11.3 volts, I was only getting about 18 rounds per second. On a fully charged 11.1 volt LiPo battery, which was about 12.5 volts, I was getting about 20 rounds per second. 20 rounds per second is exactly the same that I was getting on my previous brushed T238 motor, but that motor, as you saw before, was a lot higher RPM. For a lower RPM brushless motor, it seems to get about the same as a 1 tera brushed motor, and that's probably due to the efficiency gain in brushless systems. While I haven't tested long-term durability yet, just from this install experience, I'd recommend that you give this motor a try. It's a very competitive price, seems to perform quite well compared to brushed sister motors.